Good evening. Friday, Cinco de Mayo, 2023. Here, there's been just reading from, we're looking at Heisenberg here a little bit. In the philosophy of Heraclitus. And Heraclitus, you can point to as one of the early proponents of the dualistic monism and the establishment of the dialectic and this notions of these complementary duals. The complementary duals is sort of an analytic notion that comes up, and Heraclitus is one of the people with who is regarded this thing. In the philosophy of Heraclitus, the concept of becoming occupies the foremost place of being and becoming. And so here is reflecting kind of this state, and then the coming and going that's been discussed here in terms of continuity laws. As for conservation laws, the continuity laws establish the transitions that get from place to place. And it also helps establish the complementary dual between a boundary and crossing the boundary. He regarded that which moves, fire, as the basic element. And so this is kind of similar to Einstein in a sense. Einstein is there's no absolute motion, there is relative motion. It's elementary itself, and it's so it's elementary until you define it in the space it inhabits. It's unattached, and so Einstein has an absolute space, space-time, vis-a-vis the concept of relativity is it frees for special relativity. Otherwise, the behavior of light, like objects from the Galilean, linear. In the teachings of Parmenides, a fundamental polarity, that of being and not being, is the central concept. This reflects this dually self-infer consistency of a sort, this dually void and universal parts and collections, points and spaces, and these kinds of things. Parmenides, too, regarded the wide variety of phenomena as resulting from the combined action and reaction of two opposed principles. So for something like Einstein, we can see that shares with the usual classical principle. For every action, equal opposite reaction, assuming perfectly inelastic collisions of two bodies meeting on a line. But outside of that, it's a little bit more wide, and it's of this combined action-reaction of all the theory of some potentials. And that's kind of where we're looking at. So this is part of the introduction from, or rather chapter 1 of Heisenberg's Nuclear Physics, Atomic Theory from Antiquity to the End of the 19th Century. I just happened to leaf into this. And Anaxagoras, who followed Thales by about a century, he probably lived about 500 BC, was responsible for a definite transition to a more materialistic view of the world of phenomena. He assumed that there existed an infinite number of basic substances, the mutual interactions of which produced a variety of world processes. So Anaxagoras, kind of like Democritus, would be somebody who is one of our first atomists of sort. And it hasn't mentioned Democritus yet, but he gets to him in a minute. He assumed there existed, in his view, these basic substances possess the character of purely material elements. In a much greater degree, he conceived of them as being eternal and indestructible in themselves. And so these are like Pauli's particles, it's the material points of Einstein and these kinds of things. And he considered that the change in sequence of phenomena were produced solely by their sharing in the movement which threw them together at random. This kind of foretells the stochastic probabilistic interpretation of quantum mechanics. Empedocles, about 10 years later, saw the existence of four elements, earth, air, fire, water, as the prime root of all things. So when we talk about roots and powers, a root is kind of like what divides out. And so like for the square, there's a root. For the cube, there's a root. It's the inverse powers in a sense. So it's this complementary duals of the world of powers and the Cartesian, these roots and the scalar and the inner. There's been a lot of talk here about the inner and the outer products and the vector spaces and this kind of stuff. He regarded the primordial state of all things as consisting in an undifferentiated, homogeneous mixture of the elements bound by love in a state of eternal bliss, whereas hate tended to separate these elements and to shape out of them the variegated drama of a life. And so it's like I was reading the other day about Hardy and the beauty of real numbers, and maybe it was Russell and something about love, and that's kind of it has certain attachments to ideals of affinity and these kinds of things, the carnal, the platonic, the fraternal, the maternal, the Platonist, love and that kind of stuff. In anyways, here this is at some point kind of psychosocial. Besides that, as well, it's scientific in a sense, and it's model building. There's models of things, and so you attach phenomenological models that people can grasp with these models of physics, and then the physics. Then as soon as we start talking about the infinitesimal, it's almost like, well, how can I grasp the infinite or infinitesimal? It's like, well, it's that what exists that you cannot grasp, yet still is regular, rulil, ordinary or extraordinary. These are the kinds of things that get into building an object sense, so that something like line drawing, in Aristotle's continuum, is natural, central, fundamental, principle, and a very key component of the definitions of continuum mechanics. This pronounced tendency to materialism reached its highest development with the philosophers Leucippus, contemporary of Empedocles, and Democritus, who was Leucippus's pupil. The antithesis of being and not being became crystallized in the doctrines of Leucippus as the antithesis of full and empty. That's this notion of the Aristotle's continuum, is there's a continuum between empty and full, between 0 and 1. These iota values fill this space, and it is a space, and that's just the range of a function also. It's not Cartesian, but in the world of Cartesian functions, it's a non-Cartesian function. The concept represented by full was regarded as manifesting itself in the ultimate indivisible particles, the atoms, between which there was nothing but emptiness. The atom was pure being, eternal and indestructible, but inasmuch as there existed an infinite number of atoms, pure being could, within certain limits, be repeated an indefinite number of times. Thus, for the first time in history, there is voiced the idea of the existence of the smallest, ultimate, indivisible particles, the atoms, as the fundamental building blocks of all matter. So this is usually called the Democritan regime, after Democritus, and it represents basically our notion of atomic theory today. And most people, when they got atomic theory in school, it's like, these are atoms, and these are their sizes, and these are the orders of magnitude difference, and this is how many are in a mole, and a mole you can measure on a scale, its mass, or balance, that you can't really measure mass, you have to just balance it with something else that has a known mass, and this kind of thing. That established for the fundamentally stoichiometric, the usual ratios of things. But that and this theory are still infinitesimals, and infinity is the product of which, according to their privileged or stated or axiomatized or derived, hopefully, properties, that this one iota times this one infinity equals 1. They're inverses and reciprocals that otherwise don't exist in the complete ordered field, but they're non-standard, and that's as simple as it is. And it's simple as it is. Thus, for the first time in history, there was voiced the idea of the existence of smallest, ultimate, indivisible particles, the atoms, as the fundamental building blocks of all matter. In this manner, the concept of matter became analyzed, in fact, into 2 subconcepts. And so when we talk about this analysis, this is our deconstructivist account. This is our the pseudo, the quasi, the degenerate, that which makes it so that you can figure out how an emergent phenomenon emerges from it. Into 2 subconcepts, atoms and the void in which the atoms move. Or here it's points in space first. It's the mathematical model first is point in space. And there's a point and then another point, and that makes a space. And then the only way that the point grows is this spiral space-filling continuum, ... it's the space, and then from the resulting space you can then posit going backward from that, and that's what makes the shortest distance in a straight line. And above that, then there's the notion of the quadrants and quadrature and ... according to the Cartesian, providing Euclid's axioms as instead derived, identified components of this point in space theory, a model of a linear continuum and a dimensional continuum in infinitely many dimensions, or 1 or 0 as the point. Atoms in the void in which the atoms move. formerly space had seemed to be filled by matter, it was, as it were, stretched or expanded by material substance, and absolutely empty space had been inconceivable. Nature abhors a vacuum is the usual idea, is that it can't be, because kind of like what goes up must come down. It's that there's no emptiness is one of these usual antique physical principles. And it would help a lot of times for people to have this intuition, for their instinct to be familiar with this kind of thought process before being told something like, you live in a digital world, it's all granular to this grain specifically, ... we are ants, because it would help to have this as a usual intuition, because otherwise people will be surprised, frustrated, disappointed, resulting that they get, disconcerted, disenfranchised, ... But now, empty space was allotted a very important function. It became the vehicle for geometry and kinematics by making possible various ancient arrangements and movements of atoms. So this is still antique, since Greek antiquity. And most of this would have been thoughts and learnings coming from also before. Because basically the oldest stories, even to where they're not even the oldest written stories, but the oldest oral traditions come from the Vedas, from India, about 6,000 years ago or more. And a lot of these have also some of these same concepts. But Greek antiquity in the center there, about 500 BC, is like the time and place when a whole central history of it started. And then we fast forward about 2,200 years to the Enlightenment, and after rationalist thinking. And then it became Europe for a while, and then for a while in the 20th century it was America and higher science and all this kind of stuff. Modern 20th century science and 21st century science. Although the atom was regarded as having a special position in space, also a shape, and as executing certain movements, it was not allotted any attribute other than these purely geometrical properties. Atom had neither color nor smell nor taste, and the properties perceptible by human senses, together with changing mutations, supposed to be produced by the movement and displacements of atoms in space. Just as both tragedy and comedy could be written in the same letters of the alphabet, the vast variety of elements in the universe were regarded as the products of the self-same atoms of the different positions and different motions. So here again, you see how it's kind of framed, well, this non-phenomenological, so kind of teleological and semiotic, semi-quasi, pseudo-otic models, love and hate, dramedy and comedy, are used to help frame this dually self-inferent consistency, this dialectic, about the mathematical and geometric of these things, which really frames everything most greatly and perfectly and beautifully. The models of mathematics for mathematical physics. They say quantum mechanics is never wrong. Mathematics is physics is a mathematical science, and it's ubiquitously successful. The vast variety of the elements, regarded as the products of the self-same atoms of their different positions and different motions. Self-same atoms of their different positions and different motions. This is the notion of this, the only constant is change, geometry is motion, and these things that really reduce all this to just these fundamental axiomatic and lack thereof, axiomless first principles as final cause. Yeah, indeed. This is one reason Platonism is, when you say Platonism, it also includes a lot of these ideas that come with it. Democritus said, a thing merely appears to have color, merely appears to be sweet or bitter. Only atoms and empty space have a real existence. Now this is arguable because it's just a matter of definitions. The basic ideas of atomic theory were taken over and modified in part by the later Greek philosophers Plato and his dialogue Timaeus. Coordinates these ideas with Pythagoras' theory of the harmony of numbers, and identifies the atoms of the elements, earth, air, fire, water, with the symmetrical bodies, cube, octahedron, tetrahedron, icosahedron. This is, you catalog it by what you can catalog it by. And these were the models they had of these things that were primary, central, principal, and fundamental elements that were primary and central. The Epicureans, too, adopted the essential concepts of the atomic theory and appended to it an idea which was to play an important part in natural science at a later date, the idea of natural necessity. Natural necessity is that it's kind of like the Occam's razor. Don't be multiplying objects unnecessarily, but it's kind of like Schaffer's laser. Don't be multiplying fundamental objects necessarily, because you want independent fundamental objects, and that otherwise they're not fundamental, and otherwise they're not independent. And these are the kinds of things that add up to objects of theory. And then also when we talk about this deconstructive accounts, then it's like, well, yeah, energy is a form of interchange, but don't confuse mass and charge, two quantities that have equivalent representations of energy, as being energy necessarily, vis-a-vis what they are as when they're involved in exchange in their state. So this section really is a neat introduction to these notions that come together to form the brief scaffold of the dialectic, which is so important to critical analysis and any rational reasoning agents' possibility to escape the traps of the bombs of logic. According to theory, the idea of natural necessity. According to this theory, the atoms are not thrown together arbitrarily at random like dice, nor set in motion by forces such as love or hate, but their paths are determined by natural laws or by the working of blind necessity. This is the principle of least action these days. And the idea is to find this fundamental principle, primary fields that define, according to these configuration spaces, the field occupation numbers of these substances and their organizations of these open and closed systems in physics with regards to the conservation and continuity laws. That is then what results in the principle of least action is that as time marches on, things just naturally so follow at this point. After this point, there was no further development in atomic theory, either in the philosophy or in the science of antiquity. So this is a theory that's Platonic and separated from science. They didn't have enough of an experimental apparatus to say, we've made a millikan and measured the electron. We have electron physics now. It's just not that way. We have mathematics to add up all these current and flow models as of the discrete and the integration, and we've made definitions about Clausius and Hooke's law. No, but they do have this development of the theory that is so relevant today. It's the same models, modernized. Yeah, it's still brief. So anyways, then we'll get into modern atomic theory, and then how this is the first chapter, Matter and Atoms in the Philosophy of Antiquity. He just starts nuclear physics is one of the most recently developed branches of physics. The term nucleus was first introduced by Rutherford about 40 years ago, and the more detailed knowledge. The nuclei of atoms is only about 15 years old, but the concept of the atomic structure of matter, the view that there exist certain smallest ultimate indivisible units, which are the basic building blocks of all matter, dates back to the philosophy of antiquity, antiquity, and it was suggested by Greek philosophers as a daring hypothesis 2,500 years ago. Anybody who desires to understand something of modern atomic theory will do well to study the history of the concepts of the atom in order to become acquainted with the origins of these ideas, which now have come to full fruition in modern physics. For this reason, the following lectures, the object of which is a description of the physics of the atomic nucleus, are prefaced by a short survey of the history of atomic theory. All right, well, thanks, Heisenberg. The idea of the smallest individual ultimate building blocks of all matter first came up in connections with the elaboration of the concepts of matter, being, and becoming, which characterized the first epoch of Greek philosophy. At the very dawn of ancient philosophy, we find a remarkable statement by Thales, who lived in Miletus in the 6th century BC. He said that water was the source of all things. Geometry is motion, right? Yeah. As Friedrich Nietzsche expounded, this sentence expresses three of the most essential and fundamental ideas of philosophy. Firstly, the question as to the source of all things. Secondly, the demand that this question be answered in conformity with reason, without resort to myths or mysticism. In those times, no idea was regarded as more evident than that the source of all things must be sought in something material such as water and not in life. Thirdly, the postulate that ultimately it must be found possible to reduce everything to one principle. Then, though, that principle here is this dually self-inferent consistent dialectical monism, which is why when he mentioned Heraclitus, I picked that out because that's an advancement over what came before. in this narrative. Thales' statement was the first expression of the idea of a fundamental substance from which the whole universe had arisen, although in that age the word substance was certainly not interpreted in the purely material sense which we ascribe to it today. In the philosophy of Anaximander, a pupil of Thales, who also lived and taught Miletus, the idea of a fundamental polarity, the antithesis of being and becoming, was substituted for the concept of a single fundamental substance. So Anaximander kind of foretells Heraclitus, but Heraclitus made it abstract the concept in a sense. Anaximander argued that if only one fundamental substance were to exist, this infinite homogeneous substance would completely fill the universe, and therefore the great many varieties of phenomena would remain unexplained, and for this reason, change and becoming must have arisen from that indeterminate prime basis of all things. Anaximander seems to have regarded the process of becoming as some sort of degeneration or debasement of this undifferentiated being, or just its evaluation, as an escape, as it were, ultimately expiated by a return into that which is without shape or character, because it's lost in geometry, its motion. So, anyways, that nice little prelude to a philosophy is, the ancient Greeks and their science and their theory of the fundamental science, fundamental physics, and fundamental theoretical physics. So, we've been reading from Albert Einstein, and where we're at is kind of in the same era of Heisenberg's book we were just reading, but it was somewhat later. And I really have enjoyed this out of my later years because it really reflects, I think, a mature philosophy of science, and as well that he has had plenty of time to establish what are some of the key touchstones about how he can make logically consistent his theories of relativity, general relativity, and then special relativity, ... And then also that he makes room for his model physicist and makes room for the various things that go into energy, whereas then he gets also into the quantum theory, the continuum mechanics, which are just kind of foretold, just as it was just mentioned by Heisenberg, the ancient Greeks, about the randomness. It's not really a randomness, it's just too perfectly full of detail and information to be grasped. It still exists. The psi functions furnishes only statistical data concerning measurable magnitudes. These are the observables. That the only thing that's allowed for it to validate and not that being only to falsify or not falsify. It's not strongly validating ever the statistical hypothesis or the scientific hypothesis. It's not falsified by the observables. The reason lies not only in the fact that the operation of measuring introduces unknown elements, and here he's indicating that it's an act, it causes an effect to actually measure things, so the sampling, observer, and measurement effects are real, and because they interfere with this utterly detailed. So continuing wherever that left off, the fact that quantum mechanics of force, we'll just start here at the beginning of page 93. However, I do not believe that quantum mechanics will be the starting point in the search for this basis. Now, this was something he said about the foundations of mechanics, but it kind of is, because it's a continuum mechanics. So insofar as continuum mechanics is a real starting point, then quantum mechanics is continuation. Whereas today, quantum mechanics is the entire extenuation of the model in the physics and the atomic physics and the nuclear physics and the quantum physics. And just like Heisenberg said, well, since the ancient Greeks, they have anticipated that this would result being this theory of atomism and true atomism is of these combined being and becoming bits for being and nothing in time these days, as we talked about Kant and Hegel and Heidegger kind of. And for the space-time and the Einsteins and all this kind of stuff, that it's a most usual thing, and it's coming together kind of nicely. In view of this situation, it seems to be entirely justifiable seriously to consider the questions as to whether the basis of field physics cannot by any means be put into harmony with the facts of the quantum theory, and whether it's not, and also that it has to, it must be that they come back together. We cannot have just a fragment in physics laid out to be like, it's intractable, don't go there. There's a dragon there and nobody's ever going to see it. It's just not so. And so at the same time, Einstein is also detailing that he's just saying, no matter what, I got to have my continuous field theory with these so modeled, and because that's my attachment, and that's fine because it doesn't have to give. And so that's why quantum mechanics is never wrong until it's continuum mechanics, and then it's never wrong. As a matter of fact, up to now we have never succeeded in representing corpuscles theoretically by fields free of singularities, and there are singularities and singularities and singularities. And we can a priori say nothing about the behavior of such entities without these superwave notions or Bohm de Broglie, pilot wave, ghost wave, rest exchange. One thing, however, is certain. If a field theory results in a representation of corpuscles free of singularities, then the behavior of these corpuscles with time is determined solely by the differential equations of the field. This is basically saying that all our physics must be on the same page. Ultimately, in the same space-time and one field over it, it must be one thing. It must be unified. and here that space-time this is so different from a lot of people's usual interpretation of the Minkowski space-time, is that time is kind of free and that there exist paths in this Cartesian Minkowskian that would never exist in the model of a continuous manifold. The vector manifold of the field occupation numbers on the continuous space-time is a continuous manifold itself, or at least that it admits that that there's the normal vector at each place on that continuous manifold, and with regards to singularities, that they are closed at some point, that it's a continuous manifold or a continuous manifold with a gauge theory. That today it's called a gauge theory. So Einstein's well defended, represented, and protected here in the modern. But a lot of interpretations that followed from what otherwise are free pieces in his model and theory, unfortunately, have been incorrectly extended in a sense. And so he's also defending himself from some of his own followers in that sense. Relativity, theory, and corpuscles. I shall now show that. This is section 6. I, Einstein, shall now show that, according to the general theory of relativity, there exist singularity-free solutions of field equations which can be interpreted as representing corpuscles. So you imagine that he's just going to, like, before he established the Riemannian metric already for his general relativity, he's like, look, it's free of singularities. It's a Riemannian metric free. It's different. It's separated and divorced from this other side, but it doesn't have singularities. It's just got this contrived boundary. Sorry, and you could call that the gauge theory, part of field theory. I restrict myself here to neutral particles because, and so he's going to establish it in a milieu, and these we're going to be with regards to his particles, his material points, his space, his classical action. Because and not charged particles in the magnetic and the magnetodynamic or the nuclear particles or these things. And he doesn't necessarily and so it's either massy particles or massless particles, which are the photon. Because in another recent publication in collaboration with Dr. Rosen, and the Einstein-Podolsky-Rosen is famous for the condensed matter physics, of course. This is already kind of discussed and mentioned. Superfluid, it's in supermodels. I have treated this question in a detailed manner. And because the essentials of the problem can be completely shown by this case. The gravitational field is entirely described by the tensor G UV. In the three index symbols, gamma, UV, sigma, there appear also the contravariants G to the UV, which are defined as the minors of the GUV divided by the determinant G of the equals of the G alpha beta, the determinant notation. In order that the R, IK, the Riemannian, shall be defined and finite, it is not sufficient that there shall be for the environment of every part of the continuum a system of coordinates in which the g, v, and their first differential quotients are continuous and differentiable, but it is also necessary that the determinant g shall nowhere vanish. It's non-singular. And the eigenproblems, which eigenfunctions preserve the length of vectors so the square keeps up, so the triangle inequality holds up. But here it is not sufficient, a system of coordinates. This last restriction is, however, eliminated if one replaces the differential equations Rik equals 0 by g squared Rik equals 0. So this is the Laplacian, and he's added an extra term. It's about the nilpotent and nilvalent and these kinds of things. Whether or not that's so, it's going to depend. And that's one of the whole reasons why when we determine the metric by it's ds squared equals dx squared plus dy squared plus dz squared. They're space-like terms minus dt squared. Oh, let's instead write the Laplacian as d squared dx da 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 equals da 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 minus da 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 equals ds, the surface equals 0. So it's kind of 2 orders of magnitude above it in the differential instead of at the bottom of the differential. And then there's talk about that in that pseudo differential in the axiomatic field theory that is something like this. Differential topology. So Einstein says that he's establishing a meromorphic basis for this bit of a sort, but he'll end up having that it'll just be now it's the Laplacian's fault instead of Riemann's. This last restriction is, however, eliminated if one replaces the differential equations Rik equals 0 by g squared Rik equals 0, the left-hand side of which are whole rational functions of the g, ik, and of their derivatives. Whole rational functions. I imagine he means polynomials. I'm not quite sure. I have to refresh and understand what he means because the emphasis of the author, whole, W-H-O-L-E, complete whole rational functions, and that these are so linear also. So they're they really fit within the framework of linear analysis of is about this contravariant approach to covariant analysis, which is coordinate free because they're built in. It's coordinate free only in the sense it's absent from the transformation rules, but it's based on their coordinates. So that those are free, that you can have Riemannian coordinates and da-da-da coordinates. But anyways, this is the kind of thing that he's got so far is about making it linear and establishing that there's at least some way to think for a field that he can have a smooth answer. These equations have the centrally symmetrical solutions indicated by Schwarzschild. So the whole idea of this Riemannian tensor is like, well, when you have a sufficiently larger body, we're going to put it on the Riemannian tensor, so all its rotational bit of its gravitational content according to general relativity goes in there. Centrally symmetrical. Indicated by Schwarzschild, and the difference here is that in the inside of this centrally symmetrical, it's like on the order cubed, on the outside it's linear. It's like, well, from the outside it's like it hit a brick wall, but from the inside it's vanishing. This is a key thing about black hole physics. Anyways, and then recalling about the ds squared is what defines the metric. ds squared, little d, ds squared equals negative 1 over 1 minus 2m quantity over r of dr squared minus r squared of the quantity d theta squared plus sine squared theta d psi squared plus quantity 1 minus 2m over r dt squared. So you can kind of think of that, well, what's this 2m bit? Well, it's when mass is normalized to 1, and then there's and then it's mass times mass when it happens to equals 1, but it's kind of different. and it's in the radius and time that the metric is sort of defined this way. This is a sort of Schwarzschild's metric in his coordinates, these polar coordinates, about the centrally symmetrical solutions. This solution has a singularity at r equals 2m. Since the coefficient of dr squared, i.e. g11, in the usual tensorial index notation in the Einstein's summation convention, and that reading out a particular makes a partial, g11 becomes infinite on this hypersurface. If, however, we replace the variable r by rho, defined by the equation rho squared equals r minus 2m. So this is this implicit, the reformulated, when you send into a function an input of its own function, so you say that the parameterization is basically unparameterized that and made an entire system about above it, kind of, or that inside it happens to so collapse that results the outside system collapses, and that it's possible to contrive this kind of solution as existing, and it's called implicits, and otherwise it's pretty hinky, and that means sketchy, and but it's a thing. And so you find something like that in Mogan's work, when there was a big read up about what goes on into how he's able to supply stuff that's time dependent in terms of the function of the input, and that the location in terms of time is so derived by it. There's lots of this kind of work in differential functions, because it basically, the outputs of the functions by themselves make these things in the solutions naturally. That's their output. So anyways, here he's defined when rho squared equals r minus 2m, and you have this transformation or substitution of coordinates, we obtain ds squared equals negative 4 times the quantity 2m plus rho squared of d rho squared minus 2m plus rho squared times that quantity times d theta squared plus sine squared theta d psi squared, plus this term that for the time term, rho squared over 2m plus rho squared and dt squared. So it vanishes as rho goes to infinity, the 2m part. This solution behaves regularly for all values of rho. The vanishing of the coefficient of dt squared, i.e. g44 for rho equals 0, results, it is true, in the consequence that the determinant g vanishes for this value, but with the methods of writing the field equations actually adopted, this does not constitute a singularity. It's left out. And then, so there's whether rho squared is 0 or rho squared goes to infinity, or that mass is neglectable. That's something that would result kind of the opposite, that would behave regularly, it would behave exponentially. It is true. But this does not constitute. If rho extends from negative infinity to infinity, here it goes on, then r runs from infinity to r equals 2m, and then back to infinity. While for such values of r as correspond to r less than 2m, there are no corresponding real values of rho. Here, this is kind of arguable, because like I just said, they would just leave it exponential and out, and it helps build up this fact, this exponential versus the cube wall of the black hole, which is about the coordinates on either side of the Riemannian metric, the Schwarzschild surface, whatever you want to term in terms of this change between a linear and a fundamentally centrally symmetrical bit. It's pretty fundamental. Hence, the Schwarzschild solution becomes a regular solution by representation of the physical spaces consisting of two identical shells neighboring upon this hypersurface rho equals 0, that is r equals 2m, or for this hypersurface the determinant g vanishes. Let us call such a connection between the two identical shells a bridge. Now, a bridge is often a usual result that when you're able to connect, you're making connections. And so a bridge is a connection where transport can also happen, and interchange of sort, or exchange. And so bridge results are for transfer and the transfer principle, and so we'll call this a bridge. And then sometimes they'll be called a pont. The French word for bridge is pont. And so sometimes when I say pont after point, it's like a particular thing regards to connections in points. Here he's just indicating that there's that they essentially represent a same, and because that otherwise they would represent a different. Hence, the existence of such a bridge between the two shells in the finite realm corresponds to the existence of a material neutral particle which is described in a manner free from singularities. It's free from singularities, subject to, though, that the mathematics has underdefined bits about it. The solution of the problem of the motion of neutral particles evidently amounts to the discovery of such solutions as the gravitational equations written free of denominators as contain several bridges. In fact, indeed, for Einstein's field theory and the gauge theory, anything that reflects like a gauge that's a torsion, or anything that's like the teacup, it's the teacup here, and back to the model, that the rotational frames are free. They're not at rest, and it's free. That's a bridge. Every one of those is also a bridge. And linear and angular moments can combine. It only as they really reach each other. Kind of like when you shoot atoms at each other, from they say is like it's very, very rare for an atom to actually deflect. Because almost all the time it will orbit, the nuclei will orbit and it will swing, but it won't actually bounce one and cause that to eject from the other one. Although such a thing as spallation driven by this kind of thing is exactly that kind of thing, the disintegrator ray, whatever you want to call it, or some of these other effects. But that otherwise, when there's this kind of interference, when the atom is mostly space, it's almost entirely contrived that it's never deflection. It's always just the gravity, the sling of the gravity. What's the sling? Well, a sling is it's a loop or strap of leather, say, it forms a pouch sort of that you put a projectile in it and you swing it around and it gains angular momentum, and then when you let it go in one end of it, thus that it can cast the rock in a particular linear way, having gained such momentum. Well, that's kind of what happens in these kinds of things, but that these what that's just reflecting, though, is that when two systems with angular rotation come together, there is often, besides that they collide on the surfaces and they're outside, and so there's torsion or results about that, there's also the making way for each other, the centroids, other masses, and all that. So it's highly nonlinear, any form of usual kinematic interaction. It's unlinear, any kind of usual kinematic interaction. But it still results that is decomposed both ways into the linear and into the angular. They're complementary fundamental. It's complementary dual. Bridges. Einstein says these are bridges. The solution contains several bridges, and so the solution of this contrived formula with simple surfaces and shapes has several bridges. So the more classical a system is, the less of these sorts of contrivances are necessary to achieve a closed form solution for it. That's really what Einstein is asking for. Is I need a differential total equation. He's like, I need a closed form that's predictive and effective and successful for the success of the objects of his theory, of his model physicist. So this is agreeable. Right? The conception sketched above corresponds a priori on its face to the atomistic structure of matter, insofar as the bridge is by its nature a discrete element. Moreover, we see that the mass constant m of the neutral particles must necessarily be positive, since no solution free of singularities can correspond to the Schwarzschild solution for a negative value of m, the mass. Mass is an unsigned quantity. Energy, potential energy, is usually it's usually a signed quantity, and it's computed in terms of mass. But as a conserved quantity, mass and charge here, what make up systems of inertial systems and systems of magnetic inertial systems, are quantities, and thus their magnitudes, and so is time, thus they're never negative. Only the examination of the several bridge problem can show whether or not this theoretical method furnishes an explanation of the empirically demonstrated equality of the masses of the particles found in nature, whether it takes into account the facts which the quantum mechanics has so wonderfully comprehended. In an analogous manner, now when he says analogous, we think both of the metaphor, and also when he says analog, it means not discrete. So it's not necessarily clear what Einstein's intended receipt of this text is. In an analogous manner, it is possible to demonstrate that the combined equations of gravitation and electricity, with appropriate choice of the sign of the electrical member, the gravitational equations produce a singularity-free bridge representation of the electric corpuscle, this particle. The simplest solution of this kind is that for an electric particle without gravitational mass. This is a rather bizarre particle, because but it's Einstein's simplest solution. It's fundamentally so that given the tenuous connections between things, the tendencies and propensities of how they, attenuate and coalesce, that Einstein's simplest solution of this kind for singularity-free electron physics is not an electron, but is for an electrical particle without gravitational mass. This would be an electron neutrino of sorts or something like that. So long as the important mathematical difficulties concerned with the solution of the several bridge problem are not overcome, nothing can be said concerning the usefulness of the theory from the physicist's point of view. So long as the important mathematical difficulties concerned with the solution of the several bridge problem, or what these days is called fundamental freedom and 120 orders of magnitude about it. It's like Penrose is like, well, we kind of gave up because we got 120 orders of magnitude difference if we have all these bridges and make fundamental freedom a thing. And no, it's just to be worked back down to this superclassical wave mechanics, and hopefully it'll work out. That also then it's all orbits. It's all orbits instead of intimate kinematics, like so with the centrals and these continuity laws for this and that. Important mathematical difficulties are not overcome, nothing can be said concerning the usefulness of the theory from the physicist's point of view. But he's also got a working model of a philosopher who's also a physicist. However, it constitutes, as a matter of fact, the first attempt towards the consistent elaboration of a field theory which presents a possibility of explaining the properties of matter. In favor of this attempt, one should also add that it is based on the simplest possible relativistic field equations known today. He's like, when it works out and you need a classical approximation in the middle, come find me. And it must work with my stuff. It's like, all right, Einstein. Summary. This being the Physics and Reality, chapter 13 here. Let's see here. We began on page... It's quite extensive. Yeah, the section 5 was quite extensive. Quantum theory. And section 4, theory of relativity, pretty big. And section 3, the field concept. And then we get into the mechanics and about the Laplacian and the metric and the Minkowski and the Riemannian and that stratification of the scientific system. So this Physics and Reality is chapter 13 from 59 to 97. Summary. Physics constitutes a logical system of thought, which is in a state of evolution and whose basis cannot be obtained through distillation by any inductive method from the experiences lived through, but which can only be attained by free invention. If we point back to Heraclitus or this idea of the dualistic monism, it's not necessarily free. I mean, this is principled axiomaless natural deduction, and so it relies kind of on the consensus of the object sense of philosophers. But he is saying that there is something that can be attained by free invention. The abstract is the existence of all models. And then to pick one of those is yet and then he's expressing that there's various inductive impasses. He's like, well, if we tried to prove it this way, which we'd prove because it matches our inductive sense, we'd never reach it. It's like, really, Zeno's arrow would never arrive until you get past the inductive impasse, as an example. So anyways, the justification, and in parentheses, truth content of the system rests in the proof of usefulness of the resulting theorems on the basis of sense experiences, the empirical, the scientific method, reproducibility experiment, according to observables, according to constants, according to the finite, according to the discrete values of things that are reproducible and free from error, in a sense, in the application of the scientific method, on the basis of sense experiences, where the relations of the latter to the former can only be comprehended intuitively. As physics becomes more unified and inclusive, also, not unified in like smaller, like, well, we unified physics, how's that? We forgot it. As physics becomes more unified in universals, then it's universals, and so you have to comprehend those intuitively, but it is both of those. I mean, that's the whole idea of a theory of everything that we can attain to, not necessarily that we have. Perfect, Evolution is going on in the direction of increasing simplicity of the logical basis. Evolution of physics, Einstein says. And this is to be avoided the false or duplicitous of the false dichotomy or what is stitching? I forget if dichotomy is cutting, or maybe dichotomy is stitching. Atomicity, or false dichotomy. That there's a true dichotomy. Okay. I just made up that word, but I made it from the parts of speech that mean that word. It's like atomic, but diatomic. It's probably already word, and it's not to be carried so much, but it's where the relations of the latter to the former departs more and more from the facts of experience, and that the path of our thought from the fundamental basis of the resulting theorems which correlate with sense experiences becomes continually harder and longer. This is not necessarily so. This is the idea that it can be worked up then how to make a whole frame for all the things that then the planks and the regimes get parceled and put out to make for these experiments that according to configuration energy experiment, you have as short a form, a closed form as possible. So this long and winding road, and to make it so that we have a comprehensive route around all of physics, doesn't necessarily result then having to cast it to nobody's ever going to know, or the mountain's too big, to